All right. Well, good afternoon, everybody. So today we're going to be covering UVM. Now, as I have mentioned already, UVM is not technically a requirement of this course. However, it is one of those things that will be very helpful when you're getting a job for life. So I can almost guarantee that most of you are going to deal with some UVM thing at some point along your career. Right? It is just way too standard. There are several different versions of VM and stuff like that. So you will probably have to deal with one of these, and even if not directly one of these, most companies will have their own versions of this type of thing. So this really gets into how testing is actually done. So you are not going to be tested on this. You're not turning in an assignment on this. However, I have had students get six-figure jobs right out of college just because they knew enough, and people are like, wow, somebody came out knowing some of this, and they just hired. Right? So it can be a big difference maker. So I do encourage you to pay a lot of attention. Sorry, hold was evidently pushed on the thing. So I do encourage you to pay a lot of attention, to spend some time on this. I will be talking about ways you can modify. We're going to run a simple example here, but I'll talk about how you could take this simple example. This is kind of called Hello World. I'll show you a couple of the other examples that they'll have on a particular site that actually has some good code examples that are out there. But I picked this one because it was the simplest one that actually included all the main features. And that would be easy for you to modify to add in a design similar to like what we've done up to this point with, muxes or accumulators or things of this sort. It would be very easy to set them up. UVM is a very large chunk of handling things, right? So what my goal for on this one is to explain some of the background area, to explain why we want some of these. We have to go into the phases of simulation a little bit, which gets a little more detailed than you've seen up to this point. But we'll talk about when things happen and why they happen. We're going to have to talk about how do you block and prevent things from closing, because we're going to have a bunch of different ones. We'll have to get a little bit into dynamic memory and how do you actually do interface design inside of System Verilog. There are a few parts that get into here and some subtleties of why, for instance, do we have both modules and classes. There's going to be a little bit of kind of under the hood type of approaches to this. Now, some of this may seem extraneous, but I will strongly suggest you pay attention to the underlying theory. Here is why. If you understand why these things are happening, it will make complete sense why they do crypto things. Why do they put a function here and a task there? Why is this a class and this is a module and all kinds of other stuff that otherwise are just going to be magic. Well, all of a sudden, like, yeah, well, that's the only thing they could do in that situation. This is how it'll translate. It also will pertain to how long you're going to remember this knowledge. So if you want to be able to impress somebody in an interview, which I would imagine most of you would, and this is often, I mean, even when I got out of school, I worked in industry for a while before I went back for my PhD. Right? And when I did that, there was an awful lot of cases where I knew just enough to be dangerous in a bunch of situations, and I could talk to people, and the second I talked to them and I related my little chunk of knowledge in a somewhat cohesive sounding thing, they usually didn't know even that much, right? So the fact that somebody even knew what they were talking about was like, ooh, right? And then I would just jog it, get a book, go learn it. I mean, this was before the internet was out, dating myself a little bit, but right? But now you could go online, there are a number of good sources, and you read up on it. If somebody asks you about it, right? Don't stay at the knowledge level you're at. You know it's relevant. Build. If you do that process and you've at least got a foundation, if you watch a UVM video, they are cryptic as heck and really hard to follow. after what we're going to talk about today, if you pay attention to all the theory, you'll watch those videos and go, oh, yeah, okay. It will no longer be cryptic. You'll be able to go through whatever video you want and it'll make total sense. So that really is my goal today, is to remove the mystery, understand the basic reasons. Why are the levels there? How do they work? Why would somebody want this? And basically, what does the code look like to do it? Right? If you get all that, you'll be totally fine. Like I said, I will suggest some ways, oh, you could change this to turn this into an accumulator or other type of tester. I strongly suggest, even though it won't be tested or graded or anything else, spend like a couple hours this weekend and just do those changes. Right? If you run into problems, talk to me Monday or Tuesday or something like that. Right? Just so you've actually done it. If you actually try something and modify it on your own without anybody around to help, it will actually expose what you know and what you don't know. And if you try it a little bit, it'll actually stick in your memory long term. And you'll be in that good position where you can convince somebody, okay, be willing to invest in it. Like I said, that student, for instance, most recent one got a job just down in Austin, like I said, 6 figures type of situation, hired just because of that set of knowledge. Still doing extremely well in those areas and was able to, right, once they read it, start reading other books on it. And they're willing to do extra training and all kinds of other stuff to get beyond because they were just happy to have something to do the basics. Right? So I do encourage, it is well worth your time to invest and to keep it in your memory. All right, please log in. We're not going to be using Vivado stuff because, to be very honest, the student version, the not commercial pay extra version, cannot support this. It can when you go other, but it's too basic. We're going to be using an online website that's going to do it. Some of you might have experienced this. I've been pushing it for a few years, so I think some other people have been advertising out too, called EDA Playground. Right? So, this is one of my favorite sites, and I've been pushing the adoption across the board. It's a really good site. It's run by some, very top-end people. Their code is solid. A number of them are on, the committees to actually draft the standards and everything. So this is a really good one in DOULOS, DOULOS, right? That's another good site. But today we're going to be dealing with the EDA Playground. Now, when you come onto our Canvas, please log into the Canvas page. You'll see I have a light intro to UVM, and I also have a PowerPoint here. I would suggest you download the PowerPoint. I've got a bunch of pictures. I'm going to be walking you through it first. There's really not much text on it. It's really pictures and my commentary. But hopefully you'll see it here. But, sometimes things are not visible. Having your own copy can be helpful. If you click on a light intro to UVM, it'll take you to this page and you'll see a link to EDA Playground that automatically loads up the particular example that I want you to use. So if you use that link, you won't have to hunt for it. All right. I'm going to close this first and start up my little UVM Hello World supplementary images. So this is that first part. This is the background area on it. So I'm going to start off with, really, this is kind of more of view that you would see from a typical, test bench type design that's out there, right? The way this is, they do say UVM environment, but the way they're showing it is really not UVM. So this is more like a standard one. It does have some ideas of UVM, like drivers and sequencers getting sequences and things of that sort. But a lot of these other ideas are typical to most test benches. Now, when you've done a test bench up till now, really you had your gut, right? The idea of this driver sequencer type of stuff really was just your initial thread that was out there that walked through a couple examples. We talked about how we can make tasks to make that a little simpler. In many cases, you don't have a monitoring here. However, the framework we set up last time where we set up tasks, we can actually, as part of that task, remember we kind of set some values and wait a short period of time, usually, you know, a clock pulse or something of that sort. We could do something like wait the clock pulse and then put an if statement in there and check to see if the output is what we would have expected, because we know what the numbers were both before and after. We can hold those values, check them. And if it ends up being that it is now the correct value that's asserted, you know, we can say great, and if not, we can flag an error. All right, we'll talk about that in some future ones here. But I could do this type of monitoring where I'm trying to check to see is the result correct. As you do a lot of test benches now, right, and depending on whether you've done some of the comp-org ones, you know, we've introduced in some of those some automated testing where I can check. But if you haven't gotten into those, you haven't seen automated testing, right? The monitor is really designed to do that function, right? But if you start thinking about it, right, as you've done your testing, that's on, I have to do a lot of manual stuff. And on top of it, how do you know that you're actually getting good values for these? How do you know you didn't just miss something? For instance, what if my device under test is supposed to be for a 16-bit adder? Right? And let's say I replace that 16-bit adder with an 8-bit adder. Now, a lot of times people, when they're picking numbers, they'll do things, you know, 5 plus 3, 7 plus 5, right? That'll work absolutely great on my 8-bit adder. If I picked a really big number, you'd have some problems with it, right? But if I know exactly what tests you're going to run, let's be honest, I can take advantage of some of these things and make sure my system passes those. Doesn't mean it's good. So when you're doing this, you know, you want to not only give some sequences and check if they're right, keep a scorecard of what's going on, did you make an error, but you want to, as part of this type of monitoring, actually see, am I getting good coverage? Have I done some large numbers, some small numbers? How do I know what's going on here? Maybe even pick some random numbers to avoid having some fixed amount and monitor. What did the random number generator do? Because random number generators are not all created equal. Right? There can even be some very good random number generators that fail miserably on generating certain types of data. That's, you know, there's an awful lot of data out of this type of stuff. So just realize that's, you know, some stuff that actually matters pretty heavily. Now, on top of this, the other thing I really liked about this is that this one includes, and this is why it's really, this data claims it's using UVM because it really does, even though the pictures are simplified, is I stole this one from a MATLAB setup. Because I don't know if you know, but you can actually take MATLAB and compile it to system Verilog. Right? And I can specifically compile it for use on a particular FPGA. So I can write up my algorithm inside of MATLAB. I can test it inside of MATLAB. I can compile it for an FPGA. And I can then verify the system. I can actually hook up cables to the FPGA, program it, and I can run a test on the thing where it'll compare it against the MATLAB model. Here's some data in and everything else. I can do that same thing on a simulation one, and it runs through UVM. Right? So MATLAB will automatically generate the environments for doing that testing, and it will do the verifying the number addresses by taking results from MATLAB. So MATLAB will generate the sequences, check data, and it'll scoreboard you to see if you do a good job with it. So UVM is also the standard one used by MATLAB and a lot of other ones for automated code checking. Some kind of nice features. We feel good about basic things in here? All right. So I like this one because it's an animated GIF. This is kind of that standard setup we have, right? a sequencer, a driver, some interface. That's how you think about it. And this is switching over to what UVM is going to think about this as. Not really as just, here's my inputs, here's my outputs. What it's really going to do is it's going to take these, right? Let's see, again, interfaces. Right, the passive field. Now your device is hanging off. You have an interface that's going to cover all the different ones. Maybe it's in pieces. I'm going to have a UVM monitor which watches that interface, and a sequencer and a driver. They're all going to be part of what's called an agent. And that agent, and I can have multiple agents for part of your interface. Those agents, like you can imagine, my larger interface could have like a USB bus, it could have some other areas, it could have a clock input, all kinds of other things. And I can make different agents to handle each of the different portions of the interface. And we'll get into how that all gets taken care of. But the idea is to package that up, because really this is kind of all separated and different units don't know each other. We're going to try to package them up into agents. And those agents, we want them to understand. You're a USB system, so we're going to want the sequencer to pick reasonable sequences and the drivers to understand what are the actual rules of how I correctly follow USB. Now, this is going to be fairly complicated to set those up the first time, right? But since these are pretty standard out there, you can actually buy interfaces to all of these companies, and any decent company running this will have already done so. So when you're going to test things, all you have to do is just, here's my USB interface, and it's got the agent for that. Right? So now all you have to do is worry about what's the correct sequence data to pass into it. No work of your own. It knows the timing. It knows exactly how to set everything for it so it behaves correctly for your interface side. That makes your life so much simpler. Right? And a lot of this we're going to talk about today is going to be, very complicated if you have to write it all from scratch. But you don't write it from scratch. That's the whole point. It's designed to be very generic so you can get those modules and whatnot. That one, it just, again, it kind of shows the conversion from the other style over into a UVM setup. This is getting closer to it. It's actually only missing one major chunk in here. So you'll see there's this top test bench. I'll show you where the missing chunk is in a second. And they cut it out because in this case, it doesn't matter. It's not part of their example, so they ignored it. But that top test bench is exactly what you would have for your normal test bench. This is the typical setup. It has to create, here's your dot, right? Really, the interface is part of the dot, but we try to break it out because somebody has to plug into it. And I can tell you can see they have agents. There could be multiple. Remember I said different interfaces. Maybe this is a interface that's trying to mimic a keyboard input, and this could be, something else on it, whatever, for wherever your data is coming from. So I could have dozens of those for different plugs. It just works pretty good this way. Right? That top test bench creates an environment. All right? Now, technically, it doesn't actually first create an environment. Inside that top test bench, we'll get to it, right? We're going to have tests, right? And tests have environments. So it kind of skipped this test area. And you might say, well, inside a test bench, why do I need a test? Think about this. When you're trying to test some area, test some system, are you going to do one test on it or a whole bunch of different types of tests? Under each of those tests, might you have different setups for the system? Yeah. So that's why it's set up this way. So you might have like a batch of 20 tests you're going to do on this device you want to test. So I'm going to make a different test for each one of those, right? And each of those tests might have a particular environment. How do you plug into the interfaces? What are you setting up? What peripheral information are you giving it? Right? There can be a lot of assumptions on what's set up. If one of your things is a bus, maybe one of the things you're doing is you're going to create agents for other devices that might be on the bus that might interact with it. So you could actually have multiple things interacting with a single interface, right? Because maybe you're going out on the bus and trying to access a printer or something outright, whatever.
How do you check those? Well, I want to have inside a particular environment, which will set up what agents are out there and how they're connected together. So that's why this kind of hierarchy. In a lot of very simple cases, like you've had to deal with up till now, the test and the environment will have nothing in it other than some agents. And that's totally fine. If your environment's simple, you don't need to include stuff. But I would argue you should still keep that hierarchy. Right? So even if I'm making a test and there's nothing in my test other than my environment, I should still make a test and I should still make an environment. And the reason is, if you ever want to expand this, you don't want to have to add fundamental layers, because that's going to incorporate you having to pull extra stuff in. It just makes it a lot uglier to add stuff later on. So even if you're not using them, I really advise you take advantage of each of the layers, set them up correctly so that you can incorporate things later. All right, some basic stuff on this, right? A sequencer itself does not generate the data. There will be a sequence attached to it. Part of our construction area will be to build that sequencer loaded from memory. What a sequencer knows is the order to send them out and what pieces of data it needs to pass on here. And this one says I'm done. It knows how to load the next one up. All right? So the whole purpose of the sequencer is just to read your data sequences and know how to pass the relevant information out in the correct bundles to the driver, so the driver can, and this is actually how it's referred to, wiggle the pins. So when you listen to it, wiggle the pins just means to set the values to 0 or 1, right, or Z, or whatever it needs to do. It knows how to actually turn the number data into, the actual driven values on the pins, right? And that term is called wiggling, right? This shows it coming to the interface. It looks like the interface has extra data that's coming back out. It's not, it's really watching what's happening on this. So it's, if you have like a USB, it would be kind of like you split the cable, so to speak, right? One end is driving and somebody else is watching what you do. Because I don't just want to watch what this one says it does. I want to see what actually hits the interface, right? So we try to watch it after it's gone out, just to make sure everything is good. Did it really get it? What made it to those pins? Otherwise, your data isn't as good. So the monitor just watches what's actually hitting the interface and then passes things up. Again, that age on the other side, it doesn't matter how this is handled, right? The driver is hooked up, it's got its own sequence and a monitor. If you're not driving anything, if you're just watching on that one, that's fine. Then you just need the monitor. You don't need a driver for it, right? And it'll pass it back in, right? So you can have both sequences. You can also on that agent have reactive sequences. So imagine it's just supposed to be a device on your bus. And maybe this is like a Raspberry Pi or something, right? And you've hooked up a SPI bus or an I2C bus or something of that sort. And on that bus, maybe you've hooked a temperature sensor, right? And so now your system, right, which is you're trying to simulate your Raspberry Pi, can go out and ask, what's the temperature? So it's not driving anything until you tell it to do something. And then it's like, okay, it asks for something, what do I do? And now it pulls it across. And so there's a reactive sequence. If it asks for this, what do I send back? Right? Which could be anything. It could be a hard disk or whatever. That's what a reactive sequence is, right? It was not initiated by my driver. My driver was passive, right? So you can kind of think in some sense, right, this is the one initiating, that one's responding. Okay. We often talk about what are called the 3 C's of this. You can see 2 of them up here, right? The first one is coverage. We want to make sure, again, like I mentioned, I'm getting data and values that are checking that are across everything that matters to me, right? Makes sense with the 16-bit, 8-bit type of area. But there could be other types of stuff. Imagine I was trying to imitate a keyboard, right? You don't just want to have a lot of E's and whatever yet. You want to make sure there's a spread. Maybe you're even trying to imitate particular language stuff. Can it actually process them and group them together, or numbers, or whatever? So you want something that's going to be able to assess, was the coverage a good one, right? Maybe your particular system for some numbers, ranges of numbers, have different types of responses. You're accessing different subsystems. You want to make sure you hit every subsystem. Therefore, you want to make sure you had each of the number ranges that affects the subsystem to show up, right? That's all part of coverage. It needs to know that type of information about your system. But once it knows what the categories are, we'll be monitoring, did this happen, right? It has the ability, under the setup, not to allow you to terminate until you have met your coverage. So you could specify, I want, 96% of my categories to be covered, or I want all of them to be covered to a certain number of cases, or whatever. You can specify different cases under it, right? So the second C is called a checker, scoreboards check, right? So just like coverage, make sure you've got good data to look at. The checker is going to see, did you do it correctly? Right, so that's really what it is. Did I get errors or not? You've had to do a lot of this manually. How fun is it to look through a gigantic waveform to see if things are correct? Yeah, it's not. How error prone is it for a human being to do this? It's pretty darn huge, isn't it, right? If we're honest, we realize, I've been doing this actually since the 80s. And there are times I miss things, right? I'm pretty good at finding stuff. I know basically where to look. But you give me a really big sheet, it's pretty easy to miss something, right? This is just not what human beings are good at, right? We're good at thinking outside the box. We are not good at looking at minutia data, right? That's what scoreboards are good at. Let them track that data for you, right? So we've got coverage, we've got checkers. Our final C is constraints, right? That's not up here because it actually comes in when we generate the sequences. The sequences are generated according to constraints. Most of your data is going to be random. Right? So how does it know how to generate that? Well, you need to put constraints out there to explain how it generates the data correctly, right? It's an 8-bit number. It's a this, right? So it's an 8-bit number. It's 0 to 255, right? Lots of ways you can do these, but we have to specify constraints. So that's our 3 C's, right? All of these make up your particular test case, which really is its own little dotted line around this. And you can pull up different test cases to walk through. Make sense? That's kind of the idea of the structure. And if you look at this, when we build it, this is how we're going to build it. You will see each one of these dotted outline areas is going to be its own file with a series of stuff that will build whatever's handling inside. Okay, we are almost through the pre-stuff. This one I got just because it did a better job and introduced that one area. I was talking about multiple things on a bus. So when you read this, right, there's a single case of bus monitor here watching the bus to see what's happening. That's the interface. And then I have some that are driving, right, and other ones that are responding. Most of the stuff are going to use the classic computer master slave. I am personally not a fan of those. I saw the graphics, so beggars can't be choosers. But I prefer using client server. Right? It's a better terminology and more accurately reflects what's on. Right? These are the clients because they're requesting you to do something. Right? And these are the servers, like you might get at a restaurant. They bring you the stuff you asked for. Right? So my clients ask my device. My device, in order to answer it, asks the servers that it works with to get your data together. It packages it back up and sends its response to whatever client asked it. That's the basic setup of how buses are going to run. Yes, ma'am. Okay, so these agents here, I'm going to call them clients, right? Clients are the one that initiates them. So imagine you're running a business. A client comes in and says, I would like to buy one of your new computer systems, right? So they're asking you to do something. That's what this role is. So they send the initial drive saying, give me this. Now, when I ask for a computer system from you, you're gonna have to assemble those parts. You might not build all, right? You don't build your own hard drives or motherboards or whatever else. You're gonna go out to your servers, all your supply companies, basically. And you're gonna say, hey, I need this, I need this, I need this, right? That's all the data gathering. Then you're gonna bundle it up and give me my response. So that's basically how it works. These ones, we don't actually have those systems. So those agents are gonna have to fake it, right? And we need to know what are realistic, interactions. That's actually what's going to be covered by your constraints, right? How you set up the constraints of somebody sending a request for you, answering a request from you, right? We'll properly set up how the individual agents are going to get their sequences that the sequencers will feed. Does that make sense? Awesome. All right. As promised, the phases of simulation. I know all of you are going, oh, I like them now. Because what could be more fun than understanding every one of these lovely things? Now, in truth, this is not all of the phases. This is only the phases inside UVM. Right? So, prior to this, right, UVM phases only. Prior to this, when you tell it to run, there is the actual simulation ones that System Verilog has. They will do all of their setups and everything else, get things ready. This gets launched, there is, a run test command. I'll show you inside. Once that run test command appears, that's when you enter this, right? So your simulation has been set up and is running already by the time this hits. But I don't need to explain those 15 phases because that's not relevant. You do need to know this because each of these phases is something you might have to write some interaction from agents or other things. Conveniently, as complicated as this looks, there's actually some basic, simple areas. Let me deal with the run phases here and then I'll explain the two ends because this is the easiest one to see a pattern. You will notice that there are groups of these, right? Pre something or other, post something. Notice, right? Pre-reset, reset, post-reset. That pattern goes all the way down. So we're just going to group them into these. Most of the time, you will only deal with the mid phase of these, right? Typically speaking, this is handling whatever you need to get set up in order to do this phase. This is what happens during that phase, and that's typically what you care about, right? And this is whatever cleanup and bookkeeping is necessary to record the results from them. You might wonder why so many different stages here. Imagine I'm doing a computer, right? And my computer is initially off, right? Or it's running and it's completely wrong. So the first thing you have to do is power up or reset your computer to get into a new state. So that's what the reset phase is supposed to be. It's supposed to be whatever you need to do during the startup of your system or clearing it out of some old state to get it to a regular run environment. But not necessarily, it doesn't necessarily do anything past it. It just gets it up to the run environment, right? Configure is now I've got a running system. You want to do something, maybe you have to load some libraries, you might have to do some other work before you run your actual application, right? So this one is just get the computer up and going, right? This one is handling the whatever needs to be set up. This is when you're actually running whatever you cared about, right? And this is, my system is now shutting down because I'm done, right? So that's handling all that. All my basic tests are over, but I still need to make sure my system shuts down. For a lot of these cases, and particularly for the stuff we do wrong, I care about it. You know, like I said, those are there in case you have to deal with the full system. We feel good with those? Okay. Now, build phases. The reason why we need a build phase, because you might look at this and say, hey, isn't that what System Verilog is supposed to do when I first launched the simulation? Isn't it supposed to build things for me? Why do I have a build phase after the simulation starts when I start UVM? Well, here's the reason. When System Verilog builds things, it builds things statically. Remember, like when we're doing, you know, production, you build something and it doesn't change. But when you're doing a simulation, I might want to create interfaces and I might want to change those partway through the test, right? When you're testing something, one of the things I might do for testing is unplug a device and plug it back in and then see if it properly sets up. That is a completely normal testing area. I should test my system, right? If I'm making a keyboard, right? It'd be nice to unplug that keyboard, plug it back in and see does it come back up correctly, right? So the idea of a static system really is not necessarily built into your test. So what do I do with these type of dynamic areas? Well, I have to be able to build things when I need them. And I have to be able to unplug and plug things. So what we do is we have this idea of what's called a factory. Right? A factory builds things for you. It will build all your basic stuff during the build phase that you're going to need. And then it connects them up, and that's the end of the elaboration. So that's kind of the sequence. Get all your pieces together, have the factory build them, right? Connect all the pieces together according to the plan they told me to connect them together. And then the end of elaboration just basically does the bookkeeping and the check-in, making sure. We'll see one area like it'll publish its interfaces and stuff like that. That's classically, you'll start it somewhere else and verify it in the elaboration. So that's basically what the build phase does. I can, you know, when I'm going through tests, I can actually recall the factory partway through also and build something that will change stuff. So that's one of the nice features about this. I can do dynamic things, but therefore you can't use the standard one because it does not build dynamic things. The cleanup phase is all about, you know, doing that data stuff in scoreboard, right? I'm extracting the data that's been come out. I want to check everything they've done, send out any reports, clean it up, send it out. That's basically what's happening. And UVM is over, and that's when you get all your waveforms and everything else out. Does that make sense? We will use this because we have to build things to do these stages. There are some generic pre-stuff, but we will have to access them when we're going through. In particular, we're going to care, we're going to have to deal pretty heavily with build. We'll deal with connect once or twice. We're going to do a lot of stuff with main. Those are, for our simple system, that's going to be our biggest concerns. All right, so this one was kind of a more complete picture. So you can just see, I've got my top. There's going to be my test, which is the particular test I'm doing, which has an environment. The environment has an agent. The agent gets a sequence, puts it into the sequencer, which sends a transaction to the driver. The driver has a virtual interface, which connects to the actual interface, which is plugged into the device under test. This is a simple system. Let me just explain some reasons. Why a virtual interface? All right. Now, imagine this is a USB. All right. If I've got a USB on the side of my system, what do I need to do? Plug a USB cable in, don't I? So I would like it to look just like this interface. But why not just put an actual interface here then? Make sense? Here's the challenge. Interface is actually a command in System Verilog. And System Verilog, when it builds stuff, they are what? Static. Right? Because does it want this, you know, you're building a computer, do you want your USB port, when you look back at it, to become an HDMI? No, you build something and it's static, right? my agent's driver, does this need to be static or dynamic? Dynamic, I might plug or change things around, right? So you can't have a static thing here. Therefore, I can't have an interface there because an interface by definition is static. But I need to know the shape of that, right? What are the wires and everything else to connect it? In addition, you might have more than one bus, right? I mean, a USB bus, I could have more than one USB controller, right? How do I know which is the right one to plug into? Maybe I want to try different USB buses that are on my system to see if it works. Maybe I've got a 2.0 bus, a 3.0 bus, right? Which one do I plug into? Well, maybe I change that. So I not only need to have something that's dynamic, but I need to know where to plug it into. So this virtual interface, we're going to record for every interface we do. We're going to record the virtual interface, which can be dynamically set up and connected to. We're going to publish. This is how you connect. Right? And we're going to stick that in a database. So you'll see all those so that we can find out what they are and we can get the particulars to know exactly how to handle these. Right? So this, in a sense, like I don't like the word virtual here. It kind of is because it's not really there. When you think of virtual, you think of like virtual classes. It's not a virtual class. Right? It's a virtual interface. In reality, what it is, people will usually call it a pointer. It's technically not a pointer either, although it does point to things. It's actually what's called a handle. Have you ever heard the term handle before? A handle is a pointer to a pointer, which might seem crazy. But there's an old folk theorem in computer science that there's almost no problem that can't be handled with one more level of interaction. Right? So if you actually do a lot of programming, you will discover, it's strange, but you add a little more indirection to your thing, you can often very elegantly handle a lot of very otherwise ugly things. Pointers, one level of indirection, right? Handle, 2 levels of indirection. It turns out to do windowing and a lot of these type of, areas where I've got to swap things in and out. A handle is what you actually need to do those elegantly. So just like handling windows, I need this thing. So that's actually what it technically is, right? A pointer to a pointer. And that allows you to swap things in and out dynamically. Good? Okay, we have now talked more than enough theory. I'm going to leave this one in the background, though we might switch around a little bit. At this point, we're going to pull up our UVM setup in EDA Playground. Does everybody have this loaded? Hopefully. I'm going to try to make this somewhat big, but I don't want to fill the whole screen because I do want to be able to, at points, see this. Actually, the first one. Oh, stop helping me, Windows. I don't want you to tile my stuff. All right, I'm going to want this one first because we're going to walk through these areas inside. All right, let's start out here. Okay? The way EDA Playground sets this up, you've got your test benches, you have whatever you do. I mean, this is our device. Our device is pretty overall kind of, sketchy here. We didn't need to be very much. Okay, I can actually see the whole thing here. You might not be familiar with the very first part of this, right? So this is system Verilog only. It's not in Verilog, called an interface. If you notice, it looks like everything you would have put in parentheses because that's exactly what it is. And so we just define an interface, right? We give it a name and then you specify. The one thing you don't have on these is really directions for them. But the interface is going to basically specify everything else you would normally have imagined with it. You can actually even specify directions if you want to, but we're not going to worry about that right now. Right? So interfaces, let me kind of separate that out. Now imagine if you were doing this for like a USB bus or something that you might use in 20 or 30 places. right? You can have multiple interfaces, right? It's just like a normal one, right? I just declare it, it's now a data type, and I make an instance of it inside my parentheses that's being passed to it. So, you know, I could decide, hey, I've got 2 USB buses, I've got whatever else I want in here. So you can actually separate them out nicely and stack them. But the cool feature is if you do that and you change an interface, it updates a different way. So it does a very nice job of keeping things consistent. It also lets us do a lot of other neat things. We're going to talk about making virtual versions and everything else. Right? So, you know, just imagine I broke that all out and I put it in here. Right? Normal reading stuff. Right? I've got a clock, a reset. Right? The command that's coming in. Just think of that. This is a simple 1-bit command to kind of direct stuff. And there's an address and data. So maybe this is a bus and don't send. Doesn't really matter. They don't actually do anything with this. You can imagine whatever the heck you want. If you were going to change your area and maybe turn this into an adder, this is one of the things you would update, right? To make sure you're passing whatever the appropriate data types in. This is the actual device itself, right? They're calling it this. They actually take, you know, the interface that we declare up there, and they instantiate it. When you want to actually access that data, now the question is, what's the name? Well, it's this, you know, dot interface, diff, and then you can access it with that dot whatever you want. So you can, you know, you can imagine diff dot address or whatever. And that's what you see going on down here. Right? They don't actually do anything with this. All they do is they have this UVM info. There's different messages you can post to the console. This one's an info. Remember, you have infos and warnings and errors and stuff like that. That's all these are, right? So this is their standard info, and they just say, hey, something from the dot, here's the format string. This is old C-style stuff. But also, if you've ever had to deal with MATLAB with format strings and that all comes from C. Doing the same exact thing. Here it is. I received command, my address, data, and it's got the specifier binary. This is hexadecimal, right? And it's giving you how much they want of them, right? So it knows the size, you know, how many of these hex digits, 2 of them, right? And then comma, right? And then it passes the data through. Diff command, diff address, diff data, right? And the priority is medium. So that's all it's doing here. You send the command, it just posts the information. It doesn't do anything. So if you wanted to turn this into, you know, our accumulator, this is where you would define the accumulator, and instead of posting this, you know, you would do whatever else you want. Now you could post it and just say, here's the answers that come out of it too, if you wanted. But that's where you'd actually instantiate it. Now notice when it does this, right? In here, see how they're doing always app? Remember I told you that's not system Verilog syntax? And these are really smart people, and they're using the latest and best stuff. Almost looks like a contradict this. Except, you can't do this in an always comb. And the reason is always comb is synthesizable. Can I synthesize, post a message to the console of a computer that doesn't exist when you build it? No, right? So, will old Verilog syntax let you do whatever stupid thing you want, even if it's not buildable? Yes, it will. Right? So the only way they can post, UVM is not synthesizable. So the second they're doing a UVM here, you know it's not a legal build. But they just wanted to be able to post stuff for you because it's just a cute little example. So they couldn't actually use always comb, so they always had to use the old always at syntax. All right? And so they just use whenever diff clock comes in, read the bus and dump stuff out. Does that make sense? Now, 2 other kind of useful things you'll see. We have our include syntax. This is going to add in the package we want to steal from. This is the UVM macros, no system Verilog header. Right? So that's going to get pulled in. That is a system available one, part of the UVM definition. That'll give us stuff like UVM info and things like that. And then we also, when we're inside, that just attaches it to the project. This one pulls it in to be usable. So it imports UVM package, scoped, star, right? Take everything from that package. So you have to do both. If you just load the stuff with include, but you don't import it in, you can't use it. So there you go. That's kind of the basics. You'll see that type of stuff happen over and over. We good? All right, let's go over to the other one now. Now, this is where all the work is going to be done, right? Because that's just something to play with. Here's the actual work. This first file is going to be fairly big. The second file is also fairly big, then it gets tiny. All right, so you'll see at the very top, we include a couple things, right? So these are just some areas. The UVM macros, again, this is one of the standard ones. The next one, my test bench package, is actually the second file in the sequence. So this is how they're kind of stacking them together. That's just included. Inside the module top, this is actually your real test bench starting, right? They're calling it top. There's no parentheses going to it, so that's how you know that's the one that gets called. It then imports all the stuff from both of those, so it's available. Then it's going to go through, it's got to instantiate the interface, right? So, you know, dot interface, we declared over there, right? And it's going to call it dot interface one. And this is just kind of creating the holder for it. It hasn't done anything with it. So think about when you are actually going to make a dynamic variable, you get kind of a pointer to that thing, and then you have to use new or whatever else you want to do as you want to then actually populate it. This one is just creating the thing that's going to hold it, right? And we're going to worry about during the build stage and that handling all that process. But we now know, okay, great, build me one of these things. And we're going to instantiate the dot now. And we're going to give to it, right, you know, this, right, it's dot interface, right? So dot one dot interface, you can kind of read it that way, that's right here. And then we're going to pass this to it. So that's how you kind of instantiate it and plug in that actual interface that you now built. Now I've connected this. It was expecting me to do that, and I did. We'll set it up to how that's connected in a few seconds. Right. This just does, just like I did before, just how do you generate the clock for it? Because now we got to start worrying about building that interface for it. Get the clock initially set to 0, and then forever, you know, it's going to flip it every 5, which means your clock cycle is 10 milliseconds. That's pretty straightforward. We've done that one before. Now we'll go to our initial begin. Not too much less than this. Right? What we've got to do is that we've kind of created an actual interface that's there for it. We've got to tell people how they can access to it. This is how we're going to connect and plug things in and really make what's behind there. So to do that, we've got our UVM config database, right? This is the database of all configured stuff. Every device you have has to be there. We have to publish R1 into this database, right? So we're going to do a virtual .interface. Right, so you can notice the keyword virtual there, so it's saying this is something you can dynamically set up as needed. Right? And here's my scope again, and I'm going to set initially the null, I link it to there, right, here's my name, so it's got all the stuff, right? This is my virtual interface, there's the name, and there's my .interface one that connects me up to the actual static one. Does this make sense? Right? This is just setting up the database fields. Right? This one lets them know where that one is, so it can plug in and be able to send data to it and things like that. We can pass the stuff behind. Right? I have to be able to give it a name, which you can look it up by, things of that sort. And I have to give information. Right? It's a virtual one. And we're not worrying about all the other fields. so we just add no layers. Right? We're just making this so it knows where to find it. Good? This is all the setup, and then notice what happens. Run test. This is when my phases start. Right? So at this point, it's now going to go through and do the build. It's got everything set up for it. Right? It'll build anything else it needs, which will include a bunch of the stuff behind this. Right? And I'm just calling this one my test because that's what's going to call the next file. So it knows what to run. At the, this setup, we want to also be able to show a waveform. So this sets up what file does it temporarily store stuff in, what variables, right? We want to be able to get basically 0, starting no sublayers from the top, just dump it. Right? No higher priority. If it's a variable, dump it, we'll get it. Make sense? All right. So that is that top level one. That's what you would consider your typical thing, right? It defines whatever we've got here, and then it does the initials to set things up. Okay. Why am I not seeing? It's not showing me the whole. Sure, I'm okay with. Give me all the cookies you want. Just show me the rest of the stuff. I'm gonna log in. Maybe it's upset at me that I'm not logged in.
I need to close the down start button.
I might have to too. That's true. It should be up at the top though. You will want to be logged in. These are free for a full account, so it's worth getting. You can't save any of your work if you don't actually register for their free account. Like I said, this is one of the few places they won't send you spam. Right? It doesn't ever cost you anything, and all the files you're going to get are reliable, and they're giving you access to really expensive high-end simulators that can cost $10,000 or more. And they're actually giving you access to the full simulator. So it's actually a really amazing deal. But since the people on here are so influential, the companies are willing to do it. I got to remember what my name and password is now. Maybe. Darn it. I use my email. I set this up so long ago, I don't. Everything gets automatically pulled up on my laptop. I should have brought that. Okay, that was the correct one. I did use my email. And now, of course, it has forgotten where my link was because I just logged in. So hopefully it's remembering who I am. Okay. Why is it not showing me? Actually, it looks like the upper bar, which I still need to be able to run my code, is actually what's blocking. Okay, I just have to get it wide enough that they appear. Okay, so now you can see all the files. We'll go on to our second one, test bench. Now this one is going to have, this is where I need access to this. So just remember, right? Top, my test, environment, agent, stuff inside agent, interface from a virtual connection. That picture, please have in your easy access, because that's what's going to be related to the code. We're going to set most of this up here. Here's my test bench package. We're going to import UVM package. Again, that's the standard set of stuff. So we're making that one available everywhere. Right? You'll see we then also include my sequence and my driver. That's the two remaining ones. One's going to set up the sequence area, and the other one is the background stuff for the driver to work with. Everything else is going to get built here. So you'll see I've got an agent class, which is that innermost one. As you scroll down, let's see if I can, these are always a little bit difficult to spot in here. You can see the My Environment is also here, so that sets that up. And then if I go down, you can see My Test. Right? And each one of them, right? The My Test builds the My Environment and so on. So that hierarchy of dashed lines is handled within these classes. Now, first question to you, why do you think this one all of a sudden starts using classes when typically we use modules, and modules are like classes, right? Static. Classes allow dynamics. What do I need to do? I need to dynamically change stuff, right? The simulation is already running by the time this goes, so as far as system Verilog is concerned, even having this come into existence is dynamic. It's appearing after the start of the system. So this is all dynamic, you have no choice. One other quick difference, you'll see I've got a bunch of stuff where I've got functions here. But if you look down, you'll also see tasks. Right? Task for the run phase, right? But you'll notice that for the connect phase, I've got a function. Why this weird distinction? Why it's just all functions or all tasks or whatever? Anybody know the difference between a function and a task? I think I actually mentioned that. This is a good recall memory check. Tasks allow the clock to change. So you can have, the hashtag and the time period. You can tell it, give it a wait command. You can give it the @ command in the middle to wait for a particular event to occur. Right? Any of those things are legit. Well, when I'm in the regular run phase and I'm doing my simulation, I might want to actually have some timing things. Set this variable, wait a little bit, and do this other thing. Right? So I have to do that as a task. There's no choice. Right? A function is smaller and cleaner, and for most of these areas, when it's asking to build it, when I'm building something, I don't have to wait or anything. There's no reason for it. So function will prevent you from doing something silly like putting weights in a build, right? And if you put a weight in a build, you could actually have it completely fail. And here's why. There's no way to stop that build phase from ending. So if you put in delays, what happens, right? You're running in parallel. How do you guarantee that you finish, right? Well, if it's a function, once it starts, it must finish. It doesn't take time, quote unquote, in simulation. Right? But if you tell it to wait a little bit and then do something, the system sees, hey, I've launched it, everybody's had enough time to finish, there is no real time clock going on. So it can create a problem. So this function forces things to end. To prevent the system running before you're done under the run phase, we're actually going to do this thing called raise injection. And the system will not end run phase until all objections to ending the run phase have been removed. All right, so right at the very beginning, we're going to raise an objection. I'm doing something, and we're going to do whatever we want. And when we're done doing whatever we want, and we're going to remove our objection. And then once all objections have been removed, it goes, okay, it's fine to end. Right? And otherwise, basically during the run phase, it's forever. Literally, there is no end. Right? The only end is the system sees everybody has told me we're done, and that's just going to kill off those loops and exit out. So on the other phases, you don't want timing. It will be very bad. Does that make sense? Why the distinction between them? All right. Let's take a look what happens in these. We'll start at the very top, right? So here we've got a class my agent, right? It extends the UVM agent. Remember, we loaded up the standard UVM. All these things are standard UVM areas. We have agents and whatever else. So we're going to take the standard UVM agent because we don't want to write all this kind of junk. We just want to add in our specials on top of it. So mine's going to extend that one we already have, right? I'm going to access their component utilities and pass my agent to it, right? This will, all the standard stuff now, it's going to run through and handle everything for it. Right? I need to then set this up, so I'm going to set up inside here in my agent. Remember look at the picture inside. You've got two basic things you're going to build. You're going to build a driver and a sequencer. So that's the next two things I do. Right? I make a driver, I make a sequencer. The sequencer has to pass transactions out. Right? So think of this one as kind of like a templated class in this sense. Right? Generic sequencer, there's tons of different types of data it might be passing out. It needs to know what does an actual transaction look like for your system. So just like a templated class, you mentioned this, hashtag this, and this reconfigures it so it's following that standard, hashtag parentheses, this is stuff to modify. But just think of it like the angle brackets and those ones. All right, everybody's familiar with templated class? Yes? All right. Anybody want to take a guess what that is? That's your constructor. In a class, that's what this, function new is basically doing the job your constructor is going to do. Again, there's already kind of a built-in one, right? This is a function underneath that class. Super, just like this, refers to myself. Super refers to my parent, which is that class. So I'm going to grab that agents. Remember, I'm extending UVM agent. So I'm accessing its constructor. Its, what do I do when new, right? And I'm just going to pass my name and my parent, which is the one who is building me. And that was passed to me, right? So I'm going to take those ones, right? And I'm going to now basically register, right? This is my name, and the one who built me was this, and it just records that as a legitimate home. So it kind of knows its hierarchy of who's what. So this is kind of how that, in addition to the build hierarchy, building them, we're kind of registering it. Everything after this is now telling you what to do during it, right? During the build phase, so remember our phases, this is right at the very beginning. What do I do when I'm building? Right? So UVM phase, it'll ask me what particular phase I'm in. If it's the build phase, what do I have to do? Well, the driver, now I've got to, just like we created one to hold it, now I've got to actually build the thing and stick it into the holder that I made, right? So my driver, right, here's scope, it's type ID, create, right, driver this. So now I'm grabbing myself and I'm saying, hey, I want to get my driver, and it's basically setting this up scoped by those preset ones inside my agent, right? And so I didn't really have to do much in here. I'm just really stealing the kind of standard one that came from extension. Similar for sequencer, right? UVM sequencer, right? So just like driver, now I'm going to grab sequencer. And again, same thing, sequencer this. So all I'm doing is during the build phase, I'm saying, build me one of these following these data types that we're setting up. These are known ones. So good? A lot of this stuff is going to be very standard when you get into them. So, it's learning their names and whatever else. But if you just think of them as scoping, you'll be fine. Right? Now, I've built two things. How do they connect together? That's what the connect phase does. Build the toys, plug them together. So in the connect phase, right, I'm going to take the driver's sequence item point. Right? Going to wait 5 minutes. So I guess we are technically done on this. I will try to record the last little bit of it. You can on your own run it. So we'll say fully runnable thing.
I'll try to run through this, and that sounds like the fire alarm. When I hear an alarm go off, I'm figuring we gotta go. So I will record the last little bits, hopefully upload the video. I'm having trouble, the videos appear, but they're not letting me release them to the course. That's why no videos are showing up. I might have to just do this last bit on YouTube from my laptop. Right, just explaining a little bit. Hopefully this makes sense, and we'll see you next time. So.